the fifth video on the National 5 topic of similarity. In this video we'll be looking at area of similar shapes. What I'd like you to do is to pause the video and for each of the red rectangles here, calculate their area and write them down in the middle, and similarly for the green triangles, if you can do the same, calculate their area and write them in the middle. Right, hopefully you've paused the video and done that. And rectangle 3 by 2 would have an area of 6 square centimeters. 6 by 4 would have an area of 24 square centimeters. 6 by 9 would have an area of 54 square centimeters. 12 by 8 would have an area of 96 square centimeters. Looking at these the four rectangles, sorry, notice they're all similar. Okay, the 3 corresponds to the 6 here. The 2 corresponds to the 4. In each of these cases, they've got a scale factor of 2. The sides have been made 2 times bigger. However, that's not the case for the areas. I've started with 6, but my area is not doubled to 12. My area has in fact got 4 times bigger. Let's examine the other two and see if that's the case as well. Looking at my corresponding sides, 6 and 9, 3 and 9, 2 and 6. Well, those have all got 3 times bigger, but the area hasn't got 3 times bigger. 9 times 3 isn't 54. That's been multiplied by a factor of 9. It's got 9 times bigger. Same for the bottom here, corresponding. 3 times 4 would give me 12. 2 times 4 would give me 8. This has got a scale factor of 4. For the sides, the area is not 4 times bigger though. 4 times 6, well, it's not 96. How many times bigger is that? Depending on how good your arithmetic is, you might be able to do that in your head. Failing that, we could be doing a wee division here. Goes in once, remainder 3, 6 times exactly. The area, 16 times bigger. Looking at these numbers, scale factor of 2, a scale factor for the area of 4, a scale factor for the sides of 3, but the area's got a scale factor of 9. 4, scale factor of 16. What's the connection? Well, what's happened each time is the scale factor has been squared. 2 squared is 4. 3 squared is 9. 4 squared is 16. Let's see if that's the case with our triangles. The area of the original one, the one on the far right here, 5 times 4 divided by 2, 10 square centimeters. The top one in this column here, 8 times 10 divided by 2 would be 40. 20 times 25 divided by 2, well, half of 500 is 250. Half of 2 times 2.5, and that's just 2.5. So again, from the original 5 to 10, well, that's been doubled. 4 to 8, that's been doubled. So it's clear we've got a scale factor of 2 for my sides. My area, 10 to 40, that's been times by 4. For the middle one, 5 times 5 is 25. 4 times 5 would give me 20. My sides have a scale factor of 5. But my area, 10 times 25 would give me 250. 5 squared is 250. Sides in the second one, they've been reduced. They've been divided by 2, but that's the same as multiplying by a half. The area has been quartered. Again, that's squaring. A half times itself. 1 times 1 on the top would be 1. 2 times 2 is a quarter. Think about it. A half of a half is a quarter. So, in each of these cases, the area scale factor is the linear scale factor squared. By linear scale factor, we mean the scale factor for the lines, the sides. So, if we know the scale factor for the sides, i.e. the linear scale factor, if we know that's S, then the scale factor for area is S squared. If we think about it, lines are one-dimensional quantities, area is two-dimensional. So the squared comes from that fact there. Looking at the first pair of shapes here, well, I need to find my scale factor. I'm trying to find the area of the larger shape. So using my corresponding sides, and now my scale factor will be 6 over 2, the larger over the smaller. Give me a scale factor of 3. So the area scale factor is 3 squared. The area will be 9 times bigger. So I need to take the area of the smaller shape and times it by my area scale factor. 6 times 9 would give me 54. The green triangles in the middle. Notice the second one down here, he's been reduced, he's smaller. So using my corresponding sides, I can form my linear scale factor of 4 over 24, which would simplify down to 1 over 6. So my area scale factor is 1/6 squared. Squaring 1 on the top would give me 1, 6 on the bottom, 36. So it means my area for the smaller one is 1/36 of 270. I need to take that 270 and times it by my scale factor of 1 over 36. Now, that might look intimidating, but this has sort of been set up for you to be able to do without a calculator. Notice 27 and 36. Those are divisible both by 9. That would give me 30 there, and that would give me 4 on the bottom. So rather than doing 270 divided by 36, we're left with 30 divided by 4. Half of 30 is 15, half it again, 7.5. The heart shapes on the end here, again, I've got an enlargement. I've got 2 corresponding dimensions. I know the heights of the 2 of them. So I can put together my scale factor of 10 over 4, which would simplify to 5 over 2. So my area scale factor would be that squared. 5 squared would be 25, 2 squared would be 4 on the bottom. So I would need to take the area of the small shape and multiply it by my area scale factor. In this case, you would probably see numbers like this in a calculator paper. So you could be using a calculator for these types of questions. 30 times 25 over 4, using my SD button, 187.5. Final question. This is a bit trickier here, but I thought it was a good question to throw in. notice how there's no mention of similarity here. We're talking about a map with a scale of 1 to 20,000, but nowhere does it say these are similar. But if we think about it, a map is a shrunk down version. It's the same shape as the real life thing it represents. It's just been made smaller. So, on a map, so looking at the top question here, a map with scale 1 to 20,000. A road is measured to be 1.3 centimetres long. How long in kilometres will the real road be? So, the scale basically means it's going to be 20,000 times bigger. So I need to do 1.3 times 20,000. So times by 2, and then I would need to times by 10,000 to give me 26,000 centimetres. Now, very hard to visualise that, and we've actually been asked to answer in kilometres. So I would divide by 100, because there's 100 centimetres in a metre, and then divide by 1,000 to change metres into kilometres. So it would be useful to know these conversions. So the road's just over a quarter a kilometre long, 0.26. Here's where it gets a bit trickier with this question down here. On the same map, so using the same scale, a plot of land has an area of 5 centimetres squared. What is the area of the plot of the land in kilometres squared in real life? What I would be doing is I know my scale factor is 20,000. Now, rather than squaring that, I'm going to convert it. I know I need to work in kilometres squared, and I know that this 20,000 here would give me my answer in centimetres. So if I divide by 100, well, that's what would give me my answer in square metres. Dividing by 1,000 would give me my answer in square kilometres. So my linear scale factor, I could use 0.2, and that would give me my answer straight away in kilometres. I mean, you could check by doing 1.3 times 0.2, and that would take you straight to that answer there. So my area scale factor is 0.2 squared. 0.2 squared is going to be 0.04. So the area would be 5 times 0.04. Well, 5 times 0.04, should be able to do that without a calculator. 4 fives are 20, so I've got 0.2. 0.2 kilometers squared. So just an example of a fairly tricky question and how I've coped with some very big numbers, made them very small.